Hi there, you're in the lab with your mate JJ. Today is Maxitronix Day. Today is Maxitronix Day. We're going to keep on keeping on with our sensor robot 20, affectionately known as our 20-in-1. Today we'll be working on project number 16. This is the high water indicator. So we'll take the instructions over there and put it together in just a minute. Before we do that, we'll jump onto the computer here and just have a look through the instructions. Once that's done, we'll pop over to the booth and we'll put it together, and then once that's done, we'll bring it over to the bench and we'll have a look at it under the thermal cam and the oscilloscope and so on, just to see how it works. So let's jump over to the computer and have a look at what we're doing. Here on the computer, so just gonna open up our web browser and find our instructions, which should be here. There it is. Alright, so this is the Maxitronix 20-in-1 project 16 of 20 high water indicator. Let's open this one up here. Alright, here's what it has to say. What it does. Your sensor robot can guard against your bathtub overflowing. Wire the circuit and place your touchboard on the inside wall of your tub. Then, when you let the water fill the tub, your sensor robot prevents an overflow by signaling that the water has reached the touchboard. Note, always remain by the tub for the first few times you use this sensor, just in case you wired the project incorrectly or the board is in the wrong position in the tub wall. How it works. This circuit uses the Block 2 A-stable multivibrator. Okay. So that's this second block here. There's two blocks that can be configured as multivibrators. So this is what it's referring to here, block 2. The output of the circuit goes to the base of Q6. Again, we've seen this before. This is the base of Q6. Yeah, and it receives the output of the multivibrator. Now an A-stable multivibrator will just flip-flop between states, so it just oscillates, and the output of that oscillation is a square wave that comes through on, I believe it's a square wave, comes through on the base of Q6. Now when Q6 is on and there's a path to ground through Q5, then that oscillation will cause a tone in the buzzer up here. So as it says, the output of the circuit goes to the base of transistor Q6. If the water reaches the touchboard, which is over here, a weak current flows through the water on the touchboard. Then Q5 turns on. Okay, so we've got our touch panel hooked into the base of Q5 with a 100 kilo ohm resistor here, a 1.8 kilo ohm resistor here, and the touchpad here. Okay. So as we were saying, if the water reaches the touchboard, a weak current flows through the water on the touchboard. Then Q5 turns on, causing Q6 to turn on too. The voltage at the base of Q6, over here, we were talking about that earlier, now creates a square wave. So it is a square wave, as I said, a square wave output at the collector that goes to the buzzer. There you go. So there's a path through there now for the buzzer to buzz. If the water level goes down so that the touchboard becomes dry, no current flows to Q5 and nothing happens. So if there's no current on Q5, the buzzer turns off. Fair enough. And the wiring doesn't look too onerous. It's just 1 and a bit lines. There's sort of a line chewed up with block terminals here. Alright, cool. So let's jump over to the booth and put this thing together. Here around the booth. First things first, need to remove the cables from the previous job, so let's do that now. Alright, so that's our board cleared. It's customary to leave this one wire up here because we always need it for power. So the next thing to do is wire up the project, so let's do that. Alright, so we've got that all wired up, except for the touch sensor, which will go on these terminals here. So let's take it over to the bench and we'll install the touch sensor, and then we'll have a look at how the circuit behaves. Alright, well here we are on the bench, and let's just prop up our project lab so that the glare isn't a problem. Now we're going to want to send in some power up here, and we're going to wire in our touch sensor. Now the touch sensor should be floating around on the bench here somewhere. Did you see it? There it is. Wonderful. Alright, so I guess we'll have to get a glass of water to go with our touch sensor, and I'll use normal tap water that has minerals in it. I have some like deionized water that I use for my soldering iron, but I don't think we want to use that for this because I think the minerals help with the conductivity. I'm not real sure. Anyway, we'll just use tap water. Alright. Now I've got to fire up the power supply, so that's that. Feed out the power cables, so that's these. Now this is positive and this is negative. Now it's not on yet. Has this been wired into... It has. Okay, so we've got a knob to turn it on and off. Very good. Let's get a glass of water. I'll get that and I'll be back. Alright, I'm back and I've got a glass of water here. This will produce a tone. So let me turn the power on. Okay, power on. Then throw the switch here. Nothing should happen. And then if we put this in the water, fingers crossed it'll beep. Yeah, baby. And I'll have to dry it out to make it stop beeping. There we go. So when I dry it off, it stops beeping. Cool. What is there to see? By the way, this works just as well by touching it as it does by dunking it in the water. Well, not quite as well. If you put it in the water, it really alarms, doesn't it? Oh, it's not going off now. Oh, there it goes. If it gets waterlogged, it just stays on. Alright, that's enough, that's enough. Oh, I'm sorry for the loud noise. It's so grating, isn't it? Look, what we might do is use our old circuit board here. I put this together recently. The square wave which drives the buzzer can act as a pulse width modulated voltage source for the LED. So what we can do is we can just take one side here and let's say this one over here. Dear me, this is a bit of a mission. Alright, and we'll just pop him out. Now if we engage the sensor, we must have the polarity the wrong way around. Can just switch the wires. That's not working. Oh yeah, I've turned it off, that's why. Turn him on, dunk him. Okay, now maybe the polarity was right after all. There we go. So the waterlogged temperature sensor continues to drive the light there. Just trying to dry it out here now. I tell you what we might do is turn on the old hot air gun here, and we'll put the temperature right down. It's at 100 degrees. Still pretty hot, wouldn't you say? There we go. Alright, so that hot air gun dried out the sensor, so that's good. What if I press it really hard? Yeah, if I press it, you can see that the light goes on. So we're using the light now, the LED, the green LED, as a stand-in for the buzzer, because I find that buzzer really grating, don't you? That loud noise. And we don't need to use the glass of water. The problem with the water, it certainly works. It does what it's marked on the tin. When the water engages the tone, it sets off the tone. The problem is that this gets waterlogged and then it doesn't turn itself off, which is quite annoying. But we can just use it as a touch sensor, and if I touch it there now really hard, then you can see the green light coming on. So that will do for the rest of our experiment. And I suppose there's not much more to do. I'm interested in the voltage across. Oh, hang on with. I'm interested in the voltage across Q5, across the base and the emitter. So let me just, I'm going to put my multimeter here in voltage mode, DC voltage mode. And then I want to hook this, let's see if I can show you what I'm doing. Can you see that? Yeah, pretty much. Turn that away a bit. Is that better? Not really. There's no winning. Is there a backlight on this? There might be. There. How's that? Oh, it's too backlit for you, isn't it? Alright. Well, hopefully you can sort of see that. Now, Q5 is here, and this is the base, and this is the emitter. So I'm just interested in what the voltage looks like across those pins. So we'll put that there, and this here. Now at the moment it's not very much. It's can we put it in millivolts? I think we can. Okay, good. So it's 13 millivolts at the moment, which is not enough to drive the transistor. Now if I press the button, okay, and you can see the voltage going up, 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 up. Soon it should, oh, no, okay, it's gone over millivolt ranges. So let's put it back on voltage. And if I hold it here, it's increasing. Check it out. It's going up to 4. Come on, let's go. I reckon if it gets to 600 or 700 millivolts, yep, look, you can see that light starting to turn on. So, yep, 530 odd millivolts is enough to get a weak signal into that that LED. Can you see the green LED is getting brighter? Alright, so that's at 554 millivolts. I'm just going to wet my finger. I'll dip it in the water, and then I'm going to touch it with the wet finger. Look at that. Okay, so the voltage across Q5, the base and the emitter of Q5, has gone all the way up to 0.756 millivolts, 756 millivolts, which is enough to get a good bright signal on the LED there. So that's cool, isn't it? Now, the other thing to tell you is, and that when it stays wet, it stays. Just dry that out a bit. There we go. So it's drying right out, and it's going back down. Okay, and once it goes down to about 400 millivolts, that's not enough voltage to drive the LED at all. Now, I wanted to report that the current used by this circuit at the moment, according to the power supply, and I might be able to show you that. Let's see if we can figure that out. All right. Oh. Just having some trouble with the camera here. Just 1 second. I gotta go transform, flip horizontal. Okay, and now if I hit that, alright, so now you're looking at my bench, and if I just angle you down here, that's my power supply at the bottom there. Now that supply is perhaps a bit hard to see, but it says here 10 milliamps. You can see it's drawing 10 milliamps in its idle state. It bumps up occasionally there. It's the second number, 0.010A. That's 10 milliamps. Now when I wet my finger again and put it on the thing, you'll see that current, it's gone up to 23 milliamps, you see. I'm sorry it's not a really good view that you've got there, but that's 23 milliamps. It's using more power because it's driving the LED. So the power consumption almost doubled when the circuit engaged. And if I just dry that out again now, it'll fall back. And you can see it's back down to 10 amps again now. So there we are back on the bench. Now I did want to show you the signal out of the astable multivibrator. So in order to do that, we'll need our cable. So give me 2 seconds, I'll be back. I'll just wire up the scope. Alright, I'm back. That was actually a bit of a mission. I had to fix a bunch of things, and one of the things I did was fix that camera angle. So hello again. Sorry that was not recording the right angle earlier, but that's fixed now. I've got the scope ready to go, and I was looking at the schematic, and I want to put this scope between the collector of Q4 and ground. Is that what I want? Yeah. The collector of Q4 and ground. So the collector of Q4 is pin 55 and ground is 48. So let's try and find 55. That's over here. 55. There'll be a lot of ground pins available, but what about 48? That looks like it might be good. Where's 48? 48's all the way over here. Is it going to work? No, it's not quite long enough. Have we got something attached to 48? 48 comes back over to 67, I think. This is 48. 48 to 42. 42 follows this one all the way along to 63. Alright, cool. So let's try that. We're going to put a probe on. Put a probe on 55 and 63. Alright, and we'll hit auto on the oscilloscope here. Alright, now I've just lost my my probe. What was it? 63 was it? I think so, yeah. So I'll show you the oscilloscope. Where's that? Here. Or is that what we want to do? Maybe here. There we go. So that's the scope up the top there. And you can see this is a square wave, but it's not a particularly square wave. It sort of takes a little while to ramp up there, as you can see. And we should be able to measure, add channel 1. Yeah, channel 1. Indicator. Oh, there we go. And we want the frequency. Very good. Close that. So the frequency there is 1.62 kilohertz. Can you see that's just reported at the bottom left hand side of the screen? Actually, I'm not sure if you can see, so I might just try flipping you over there. So we've got the frequency measurement. That's at the bottom left. And you can see the square wave. Now, I've said this before, and I guess I'll say it again. One thing to notice about the A-stable multivibrator is that it's always on. It's always generating its tone, which comes out over here on pin 55, which is what we're looking at on the oscilloscope at the moment. It only buzzes when Q6 allows. The light's not on at the moment. If we press the touch screen, what's happened here? That should be glowing. I must have knocked oh no, it was just a matter of getting enough moisture on the touch sensor. So you can see that the it's interesting that whether the LED is on at all or not has very marginal. You can see. Can you see that as the green light goes up, the peak of the square wave just comes down a little bit. So you see the green go up and the peak comes down. Green goes away, peak goes up a bit. And I suppose the other thing to show you is the thermal cam. So let's do that. Where are we for thermals? There we go. Thermals. So you can see, and this is a feature which is really quite surprising. I'm always surprised by how much juice this multi-vibrator circuit chews up. and you can see here and here are the resistors, and those are really quite warm, aren't they? So there's a little bit of a reflection, is it? Here? What's that? Not sure exactly why that's glowing point. So you can see some reflections off the terminals, but the really warm thing is the multi-vibrator resistors. If I move this across, there's not much to see on this side of the board really, temperature-wise. So that's interesting. These resistors aren't chewing up anywhere near as much juice as the ones on the left are. Interesting. So I think that concludes this project. Is there anything more to show you? I don't think there is. So we'll take you over to the farewell cam and we'll wrap up. That's a wrap. So today was the high water indicator. We learned that when the sensor gets wet, it does trigger the alarm, but drying the sensor out again to turn the alarm off is a little bit of a hassle, isn't it? It also the sensor responded to the touch, provided the finger was wet. So I put my finger in the water and touched the thing, and that was enough. About 750 millivolts seemed to be the top end of what the circuit would deliver to the transistor base, which controlled the amplifier on the output of the astable multivibrator. So again, under the thermal cam, we saw that the resistors in the multivibrators, which are variously 10K and 1K. I think it was the two 1K resistors that were generating the most heat. The 10K resistors didn't generate much heat at all. So there was hot 1K resistors. We saw the output stage. It was a 1.6 odd kilohertz thing. We showed you the frequency measure on the scope, the oscilloscope, and we noticed that when the LED was consuming power, the top voltage reached by the square wave came in just a little bit. So and of course we attached that LED instead of the buzzer, because the buzzer makes just a grating racket, so it's easier to look at the green LED. So yes, okay. Just another experiment, getting more familiar with our astable multivibrators. That all seems, we understand that pretty well now, and how to use the transistors as a switch. Very interesting. So I think that's it. I hope you enjoyed this video. Thanks very much for watching, and please remember to hit like and subscribe.